Hello there. Hey, let's look at section 8.1 tonight. I'm sorry, it's tonight for me. Integrals as net change. Mainly what we're going to focus on here is the linear motion revisited. So this gets us started into unit 8, which is all about like practical application, but application of integration. So we will get into area between the curve. That's the next section. We also get into volume of revolution, all things that we touched on a slight bit last year. So here we go. Let's look at this first one, and it says, "Ooh, I gotta move me." It says velocity equals 10 minus 2t is the velocity in meters per second of a particle moving along the x-axis when t fits between 0 and 9. Use analytical methods to determine when the particle is moving to the right, when it's left, and when it's stopped. So what would I do for this one? Well, I would take my velocity function and I would try to factor it. I'd pick up my critical points. Remember, that's when we set it equal to 0. And then I'd probably do a little sign chart on this, and I know my bounds are 0 and 9, so maybe I'd put those on there just as a reminder. I would pick a spot on each side, left and right, of 5, and see what the sign is. So if I put in 3, looks like I'm positive here. Let's get a different color going. I'm positive. And if I put in 6, let's say, I'm going to be moving negative. So when is it moving to the right? It's moving to the right on the interval 0 to 5. It's moving to the left on the interval 5 to 9. And it is stopped at t equals 5. Find the particle's displacement for a given time interval. And our time interval was between 0 and 9. Remember, displacement is the actual net distance moved. So it takes in account if I had gone 5 to the right, 3 back left, followed by maybe 1 to the right, my net position would have been 5 minus 3 is 2, add 1. I would have finished at a location of 3 had I started at 0. So that is displacement. It takes the positives and the negatives and gets just the final outcome of the result, going forward, backwards, forward, whatever. Find the particle's displacement for the given time interval. So I can really just do an integral on that time frame 0 to 9 of my velocity function, right? Because if I do velocity function, the integral turns out to be position function, right? Moving upward in our thought process. We start with position, take a derivative, we get velocity, take a derivative, we get acceleration. So if I move myself back up the scale, I'm going to get position evaluated from 0 to 9. And that means that by fundamental theorem, we get s of 9 minus s of 0, which is how we calculated it before we knew about integrals. But this would give us the net position. Where did I start minus where did I finish? That tells me what my net movement was. So particles displacement. I would just put this in my calculator. Well, this one would be fairly easy to integrate by hand. I'm going to try and remove that because I just wanted to tell you about integrating velocity, remind you about that. So I would integrate 10 minus 2t dt, and that's going to give us 10t minus t squared, evaluated from 0 to 9. And looks like we got 90 minus 81. Put in 0, that gives us 0. So it looks like I have net displacement or particles displacement as 9, and we were in meters, so 9 meters. Okay. If s of 0 equals 3, what's the particle's final position? To get final position, I'm going to take the initial position plus the displacement, how the the change of location, right? The change of position. And that's what I need to do. So I'm going to say that, you know what, I want to take back one thing. Well, let's do this. S of 9 will equal S of 0 plus the amount of change that we had from 0 to 9 of V of t dt. And we remember that S of 0 was 3 added with what we calculated in the last question. And we're going to get the final position would be location of 12 meters to the right. Yeah, that works, doesn't it? Find the total distance traveled by the particle. Total distance. Now, this is the one that's kind of a pain, unless you have a calculator. If you have a calculator, it's very simple to do because we can wrap those absolute values around our velocity function and come up with the answer. So if I were to do this in my calculator, 0 to 9, absolute value of 10 minus 2t dt, I would get an answer, and unfortunately, I hope I have it here because I didn't put it in my calculator. It looks like we should come out with 41. Now, if I had to do this, yeah, this is the part I wanted to explain to you. If I have to do it by hand, I've got to be really careful because we know that by our sign chart up here, that our particle, darn it, why does it do that? Our particle does change direction. And when it changes direction, it affects the sign of the movement. So this would have been positive movement, this would have been negative movement, and it nets out to give us displacement. But now what I want to do is, when asked about the total distance, I need the absolute value of that distance traveled and the absolute value of that distance traveled and sum them up so that I get the total amount of distance covered. So I'll take my sign chart and create individual integrals on those time frames that I know I have the change going on. So from 0 to 5, I need to evaluate the velocity function, and from 5 to 9, I need to evaluate those. The only thing I can see that I'm not liking on this is the fact that there are not absolute values thrown on each side of those integrals. So now I've got to move the absolute values to the outer portion of my integral so that the result I get, actually this would be the one that's going to come up with a negative result, so that I can flip that result positive. So absolute values have to be outside of it. When our calculator does it, it does it in this manner for us, but does it automatically, if that makes sense. All right, number 11. Projectile. Recall that acceleration due to Earth's gravity is 32 feet per second squared. From ground level, a projectile is fired straight upward with velocity of 90 feet per second. So, early in AB, we learned a position function, and that position function looked like S of t equals 1/2 of acceleration t squared plus v naught t plus S naught. And that is a beginning position function. We could work our way up from acceleration and integrate and come up with that, but I'm just going to let you start from that position function. This should look very similar to what you work with in physics. The only difference in physics is they talk about change of position. So I think yours might go change of x equals, and it'll have this stuff, but not the S naught. Because what's happening over here is you've got ending position minus beginning position equals 1/2 AT squared plus V naught T. And ending position minus beginning position gives me change of position. So that's how it relates to your physics formulas that you have on your sheets. Number 11, recall. Okay, so we got Earth's gravity and it's fired straight upward with velocity. So this 90 feet per second is V naught, or V of 0 is 90. And since it's upward, we know that's a positive 90. Earth's gravity, our A, is equal to negative 32. Since it's a downward force, it'll get the negative. What is the velocity after 4 seconds? So I know that V naught is 90. I know that A is negative 32 feet per second squared. And that allows me to write a position function of 1/2 of negative 32 t squared plus 90 t, and plus I need to figure out what was its initial position from ground level. That is an indicator then that S naught was 0. So I can fill in that as well. If you're keeping track down here, S naught was 0. Started at the ground. So we get this function here. And what is the velocity? So I know if I take a derivative of position, I get velocity. And half of 32 would be 16, so that's negative 16. Multiplied by 2, because I'm doing power rule, so negative 16 times 2t to the first plus 90 brings me back to negative 32t plus 90. Then go and evaluate it at 4, of course. S prime of 4 equals 32 times 4, 120, 128. So negative 128 plus 90 gets me negative 38 feet per second. So obviously, this would have to be, since the velocity is negative, this would be in the downhill part of the parabola. When does it hit the ground? Well, when is a time question, isn't it? So I'm looking for time, t equals something. When does it hit the ground? Well, ground tells me that the position, I'm going to write ending position equals 0. So now I can take the position function, S of t, and set it equal to 0. And S of t I've got written over there on that other side. So what was that? S of t. Let's make this negative 16t squared. Oops, slowing down big time. What the heck? Every once in a while it just gets stuck. Anyway, I wanted to see if I can erase the ink and see if that would help. Okay, so we've got this negative 16t squared plus 90t. We're going to take that and set it equal to 0. So for part B, we have 0 equals negative 16. Could definitely take out a 2, couldn't I? What is happening? 0 equals negative 2. I'm going to pull a t as well. And that's going to give me 8t minus 45. So there's 2 times when the position is 0. Obviously, when we started, oh, I know what's going on. I must have clicked the text tool. Check that off. Okay, so undo. What I need is to get back to my function there. There we go. Time equals 0, or time equals 45/8. And since it wants to know when does it hit the ground, it'd be at 45/8 seconds. When it hits the ground, what's its net? What is the net distance it has traveled. So net distance, obviously, our function goes up and then back down. So the net distance it's traveled is 0 because it starts at 0 and it finishes back at ground level. So even though it traveled this, the whole path would be our total distance traveled, but the net distance, it hasn't changed its position from its starting position. So its net position is 0. When it hits the ground, what's the total distance it's traveled? Okay, there it's getting that total distance. And what I might be tempted to do on this one is just, it took 45/8 to travel the whole amount. So what would happen if we did an integral from 0 to 45/8 of our velocity function, absolute valued, it's slowing down again, dt. That should get you the total distance. I'm coming up with 253.125. 253.125. Remember, you always got to have 3 decimals of accuracy. All right, we're going to see if we have better luck with this screen. In exercises 12 through 16, because this was taken out of the textbook, a particle moves along the x-axis, units in centimeters. Its initial position at time 0 seconds is x of 0 equals 15. The figure shows the graph of the particle's velocity. The numbers are areas of the enclosed region. So those little numbers that we see, 4, 5, and 24, represent the area between the curve and the x-axis. So this is the velocity function shown. If I were to integrate velocity, I can remember that that's going to get me position, isn't it? And that'll tell me how far it travels. So the integral under the curve is representative of the area. And we get into area a little bit more in 8.2 as well. What's the particle's displacement between time 0 and time c being right there? Well, since it's displacement, I don't want to absolute value it. I would just say, what I wanted to do was I'm going to write 0, a to c. No, it was 0. From 0 to c of v of t dt, that's equal to displacement, and that's going to be a 4. But since it's below its negative, plus a 5 minus a 24, and that adds up to negative 23. So it has moved centimeters, negative 23 centimeters. So that means it's to the left of where it started. What is the total distance traveled by the particle in that same time period? Now what I would have is an application where I go 0 to c absolute value v of t dt, which would result in absolute valuing each of these little pockets of movement. And I'm just going to continue to show all 3 absolute valued, even though that middle 5 wouldn't have been totally necessary. I get 4 plus 5 plus 24, 28 plus 5, 33. 33 centimeters is what the total distance traveled was. Give the positions of the particle at times A, B, and C. The position of the particle is going to depend on where it actually started. Did our particle start at the origin, at position 0? Well, to do that, I need to go back and reread for more information. Its initial position at time 0 was 15. No, it didn't start at the origin, did it? It started 15 units to the right. So the positions, it's going to be S of 0 plus the change of position from 0 to A of v of t dt would give me 15 plus the area under the curve between 0 and A is a -4. So now, because it moved backwards by 4 units, I'm at position 11, right? And I could kind of just keep working forward from this, couldn't I? I could even write its position S of A plus the position A to B, look at that, V of t dt, would be the 11 that I left off at when I was at A, plus the 5, getting me to 16. My position for S of B is 15. Now I could pick up from S of B, couldn't I? S of B added with the movement between time frame B to C, V of t dt, would be where I left off. S of B was 16, and now we're backing up 24 units. We are going to end up at -8 as a position. And this does mean 8 units left of the origin. Approximately, where does the particle achieve its greatest positive acceleration on the interval? So acceleration is the rate of change of velocity, or it's the slope of velocity, right? So I want to know where the slope is the greatest. Oh, and it's got to be positive, so it needs to be increasing, doesn't it? Where is velocity increasing the greatest? Well, I've got a slight, I'm kind of looking at tangent lines here and comparing slopes. Positive there, positive, positive, positive. It is the greatest at time equals c, because the slope of the velocity is increasing, or is the largest. Number 16. Approximately, where does the particle achieve its greatest positive acceleration? Oh, darn it, I didn't read this well enough. My answer was for 16, wasn't it? I got to go back. On 0 to B, this would be time frame A, just what I had written, right? Time frame A. This one is at time frame C when we expanded that interval to include 0 to C. All right, hopefully that makes some sense. The last thing says the graph of the velocity of a particle moving on the x-axis is given. The particle starts at x equals 2 when time equals 0. And find where the particle is at the end of the trip. I'm going to come back to this again. I know what I wanted to do earlier. If I integrate from A to B of V of t dt, we realize that gives us S of B minus S of A. Position at B minus position at A, because velocity integrated gets its position. When I add S of A over to the other side, just think algebraically here, I get S, I think it's my ring that goofs up, S of A plus the integral A to B V of t dt equals ending position S of B. That truly is where that initial position plus change displacement equals ending position. That's where that's driven from. So where will the particle be at the end of the trip? I need to know, where did it start? Okay, it started at 2. Because for us, it's going to be between, I'm never satisfied, am I? I want to make it really abundantly clear. It looks like we go to 10. So S of 10 will be equal to where I started, S of 0, plus, now I need my integral beginning spot to match where I left off with that position. So those should be a matchup, shouldn't they? 0 to 10, V of t dt. And S of 0 is in the write-up, so go read carefully. Looks like we started at 2, and then we got to pick up all this position work. 0 to 10, V of t dt. How do I get V of t dt? I'm going to use the area under the curve thing. All right, so I go back over here. Unlike this nice little example where they gave us the numbers, they did not give us the numbers on this little problem. So we got to calculate it ourselves. And you're pretty good with triangles. So 1/2, we know the area of a triangle equals 1/2 base times height. So in this region, I would have 1/2 of 2 times height of 3 gets me a 3, doesn't it? Okay, now we got our little area there. And then I want to probably calculate out this trapezoidal area. You can do it however you want. I'm going to do trapezoidal rule. 1/2 of the height of the trapezoid is 3. The distance on this base is 1, 2, 3, 4, 5 units. The distance here goes from 6 back to 3. That would be 3 little units. 8 times 3 is 24. Half of that is 12. This looks like a -12 region. And then here, what would we have? A 1/2 base area. 1, 2, 3 spaces. 3 high. Looks like a 4.5 to me. And now I bring that into my body of work. I get a 2 plus. Wants to know where it's at the end of the trip. That means I'm working with displacement. So I'm going to use the positives and the negatives with no absolute valuing it because I'm not after total distance covered, plus a 4.5. What does that get us? A -10 with 3 would be -7. -7 and 4.5 gets me a -2.5. I think that's right. If I did my math wrong, I'm sorry. Part B, find the total distance traveled by the particle. Oh, hey, of course they asked that next question, right? So I'm just going to erase that last calculation so I have some space here. Total distance covered, this is going to be a piece of cake because we already got the work set out for us. Total distance, I need to absolute value each of those regions. And this would be sufficient for the AP. And now we got to add up, what, 12? 12 and 3 make 15. 15 and 4.5 make 19.5. And they don't have units, so just 19.5. All right? Hopefully that gives you a quick recap on linear motion, using integrals to help us with the net distance and the distance traveled. So I've gone in and tried to find, this is not the easiest thing to find, some problems on WebAssign that get to these sort of questions. And I actually pulled it out of a different textbook. So you're going to be working these 8 problems on WebAssign. So good luck with it. I think I gave you 4 tries on each. So hopefully that allows you to get help if you need it. Good luck.